So what we're going to talk about today is hardware acceleration for FHE. And so just to come back to what FHE is, or what the problem is we're trying to solve, is essentially the data paradox. So data paradox says that on one hand, data is the new gold. We can do amazing things with data. You see this with the AI boom, but think more broadly, like medicine. If we can harness all the medical data that is available now, that will be really cool. We can do like medicine research, personalized medicine. In the financial space, you can also do amazing things if you have all this data, if you can collect all this very high quality data. But on the other hand, we have the problem that there is data protection, privacy regulation. We realize that you don't just want to give your data away, right? Your medical data, you should not just put your DNA data on the internet or put your financial data on the internet. You don't want that. And so this means that we cannot use this very high quality data to do all these amazing things. And so the question is, how can we use this data without disclosing it, without just giving away this data? And so one way to do this is fully homomorphic encryption, or FHE. So FHE allows you to do computations on encrypted data. We've already established that. So what does this look like? We have a data owner, one or more data owners. They encrypt their data. They send it to a server, to anybody. And this server will be able to do computations on the data. Now, importantly, nobody, even the server, will be able to see what the underlying data is. So you can do all these computations, but you're just working on data that doesn't mean anything to you. And in the end, only one party, the designated party with a secret key, can decrypt the end result of the computations. And this allows you end-to-end confidentiality. And so what we can do with this is really unlock data value by guaranteeing privacy and security. I mean, don't think about an application that exists where you can build this extra layer of security on top, which is cool, you can do this. But really think about the applications that become possible. Like, you can go to a hospital and say, I want to do this medicine research, and I can guarantee that your medical data of your patients is not going to be leaked. Like, you can provide guarantees. So this means that there's a lot more applications that become possible. Right? Because you can guarantee to people that their data will be secure and they will be much more willing to grant you their data. Now, if we look at FHE, the state of the art, it's an upcoming technology, and the advantages are really clear. We have this end-to-end confidentiality, which is, by the way, post-quantum secure for everybody who knows what that is. And it really allows this very cool new applications on medical data, on financial data, on all this very high-quality data. But at the moment, there's also still some barriers to adoption, and that is why we're seeing FHE only now getting traction. And the two main barriers to adoption, I would say, are usability and cost. So in terms of usability, working with FHE used to be highly technical. It used to be something for cryptographic engineers, really people that knew the insides and outside of FHE. This is improving at a very rapid pace. So there's new tools available now, and it's a really exciting time now because you can download, for example, any of these libraries, like the Zama library or the OpenFHE library. You can download it and play with this and program it yourself. You don't have to be a cryptographic engineer anymore. You can do this by yourself. So really try it, like in this afternoon, download one of the demos from the Zama library, for example, play with it. It's really cool. And so I think this usability barrier has been solved or is being solved at this moment, and really play with these features. Now the second thing is the speed. So how can we get FHE to a speed where it's actually useful for a lot of applications? And there has been a lot of work in this area done. We have like new schemes that have been developed, a better fit of algorithms. There's like improvements to FFTs and entities, all of these arithmetic things that you can do. But in the end, you hit a certain barrier. You hit a barrier and then you want to still improve. And then you need to look at compute platforms. So typically now all of these things are run on CPUs, maybe on GPUs, but you can go further. You can go to FPGAs or maybe even your own chips. So that's something where you can really gain. Every time you go from one compute platform to another, from CPU to GPU, you can gain about a factor 10. If you go from GPU to FPGA, you can gain about a factor 10. This is the typical thing in industry. So what we want to do is actually go from these CPU, like very general, flexible, easy to program compute platforms to the right, which means that these are compute platforms that will give us more efficiency, but also they're harder to program, and they have less flexibility and all. So we want to actually move there, but it comes at the cost of a certain engineering effort. This is just an example of all of these hardware platforms. Now in this presentation, I'm mostly going to talk about FPGA. So what is FPGA? It's essentially programmable hardware. Like if you make your own hardware, you put all these gates on a chip, you connect them, and you let it print in a factory. What an FPGA is really a board with all of these components already on, and what you do as a programmer is connect them as you wish. So you put the connection between the gates, but all of the gates are already there. What is the advantage? Why would you program on FPGA? Well, it's programmable, which means that you can really easily adapt to algorithmic changes, to new parameters. You have access to the newest, fastest version of the technology in a day. So we can reprogram this, starting from your code to reprogram the whole thing. It's in a day you can do this, right? So that's really cool, because if you make a chip, that takes you at least half a year before the chip comes back. So you make the chip, half a year later your chips come back. With FPGA, after 1 day, you have a new version that you can try out. The cool thing is that this is built on the latest technology node, so it will give you actually quite good results. And especially it is available in the cloud. You don't need to make your chips and then sell them, and if you don't have enough chips, you have to wait. No, I mean, Amazon Cloud is there. They have this FPGA, so you can just run it in Amazon Cloud. You set up an instance, and if you need 100 instances, you do 100. If you need 1,000 instances, you do 1,000, right? So you can really scale with demand, which is a really cool thing of FPGAs. We can also do this on-premise, right? If you don't want to run this on Amazon Cloud, if you don't want to run this on Azure, Microsoft Cloud, then you can just run it also on-premise. We can buy these FPGAs. Now we see hardware acceleration really as an enabler of FHE. If you look at AI, this is an invention from the 1950s, right? Neural networks have been invented in the 1950s, and essentially nothing happened with this technology until in the 2010s, where we actually had the compute power to use this technology at the high level. And this is really when we have this massive boost of AI. Because we have this computational power, because we have this dedicated chips for AI, we see that it becomes a technology that is actually feasible to use. And the same thing we've seen with zero-knowledge proofs, right? It's an invention from 1985. It was a really cool idea. People were working on it, but then you see that the real breakthrough comes when the hardware is available, when computational power catches up with what we actually want to do. And the same thing is happening with FHE. So at the moment, we're really making FHE cost-effective and fast enough to be used in real-world applications. So who are we? So we are Belfort, and we are a company that is building hardware acceleration for advanced cryptography, and our first target is the FHE, which is one of the FHE schemes. So we're a team that is rooted in cryptographic hardware research and design, based on years of leading-edge research in the COSIC research group, which is, for example, responsible for the AES standard that is used for encryption everywhere worldwide. And at the moment, we have the first available FHE accelerator that you can play with. If you want to try it out, please contact us. So we have this accelerator. What can we do with this? Well, if we use this accelerator, we have 123 times speed up versus single-thread CPU. That is what people are using to compare these accelerators at the moment. And further speed-ups are coming. We also have fast scalability, so we can deploy this on Amazon Cloud, as I said before. We can deploy this on-premise, whatever you want. And we integrate this library into TFHE libraries so that it's easy for you to use. And I will come back to this later in the presentation. So as I said, computing on encrypted data, TFHE is expensive. And this is essentially expensive because there's two main functions that are responsible. There's a bootstrap and a key switch. And it's really these functions that we're going to accelerate. And if you look at our accelerator, it looks a bit like this. This is a high-level overview. And I will not go into details here. There is technical talks out there if you want to see how this works in detail. But I'll give you kind of an overview, like an ID, high-level ID of how we do this. But essentially, we have three key innovations. We have a streaming architecture, something that I will explain. We do batch computation, so we take multiple inputs so that we can have massive parallelism. And we do fixed point representation. What we do is we really try to cut out all of the unnecessary gates that we don't need. So we try to really optimize to a bit level on where we can cut things, we really cut them. So the idea of hardware is really this. So on the left, you have a CPU. This is a normal processing unit that you have in your smartphone, in your computer. And what essentially happens is it will do some calculations according to a certain recipe. So it will first fetch an instruction. It will fetch, what do I have to do? This will come from memory, and then it will read, now I have to do an addition. So it will fetch the first thing of the addition, the second thing from memory, then do the computation, and then set everything back. As you can hear, this is a very cumbersome process, right? So in hardware, we take a completely different approach. What we do is we send all of the data that we want to compute on to the hardware, and we will start to compute on this. We will start to compute the first operation, the second operation. But the cool thing now is once we've passed the first operation, we can already send the second part of data and start to compute the second operation. And once these operations are done, we can push the next one. So compare this, a CPU is essentially like a craftsman, a very experienced craftsman that can do all of these cool things, but every time he has a project, he has to come back and do these calculations on the do these operations and put the project back. While our hardware is more like a car manufacturer, right? So there's all of these stages. You push in the data, the car. You do the first operation. Once the first operation is done, the second car can already come in. The third car can already come in. And we can have this massive parallelism to compute on. And you can see this. So at the moment, we have a first version of our acceleration, which is not meant to be the fastest ever, but just to have a working version. And so you see already with this version, we can do 175 8-bit multiplications per second. While on our FPGA setup, we can do about 250 multiplications per second. But this is only the beginning. We know from here how we have to scale up. And by the beginning of next year, we will be able to have a factor 10 speed up and do 2,000 operations per second. And then by 2026 or 2027, we will be able to do 20,000 multiplications per second. Really by scaling up because of this massive parallelism in the hardware. And so that's how we aim to make FHE actually affordable, right? By providing these speed-ups and also in the same vein by providing these, by reducing the costs because of this. Now, let's do an application, right? Because we want to also show that we can actually use this hardware in a real-world scenario. So what we've done is we've took this application, which is trivium transciphering. It's an application that you can use to reduce the bandwidth. So if you want to send data, to an FHE cloud or to the blockchain that is using FHE, you could use trivium transciphering to reduce the data. And we've built a demonstrator that I will show at the end of the presentation, hopefully. I mean, it's a live demo, so let's see what will happen, to do this. And this is the time factors on our server. So we can do this on software, where we get like a certain execution time. And then if we do this on our FPGA setup, we can speed this up by a factor 300 compared to our quite good server at home. So this is something that we will show later. But first, And lastly, I want to go in how do you use this accelerator. What does this look like? So if you want to come to us and you say, I want to use this, what do you do? Well, first what we do is we have to choose whether you want to run it on Amazon Cloud, which I think is the easiest way to run it, or you want to have your own server in your basement. That's also fine. Then you choose any supported library. You don't want to write this crypto code yourself. So just choose a library that you can already play with. And as I said, you can already play with this library, so please do. It's really cool. And then you can use essentially our Belfort API to speed up this whole process. And what this looks like is if we go to these libraries, we have computations like this. So we have, for example, a key switch bootstrap. This is the one that we essentially need to speed up. We just replace it by our own call, which is key switch bootstrap packed. And the only thing you have to do is patch multiple of these operations together. But this is maybe a bit too technical. So we also provide a higher level integer API. So in this higher level API, what we do is essentially you write your code as you're used to in this library. So you write exactly the same code as you've always done. And the only thing you have to change is in the beginning, you change one line of the code and we handle the rest. So this means that you can use any library that you've played with. You just submit one line of code where you say, I want to actually run this on FPGA. And then you can type in a multiplication, type in an addition, and it will automatically be run on our hardware. This is an example of a FHE library, but we can do essentially any other library as well. So if you say we really want to use another library, yeah, just come to us. We can work together to create another library, to create access for another library. So now it's time for the demonstration. What can we do? Let's see, you see this? Perfect. Okay, so let's see. So we have this application that we want to run. And yes, live demonstrations. Okay. Okay. Okay, so we're in the system. So I SSH'd out to our server in Leuven. And what I will do is run first this application on this server on 32 threads. And it will start running this application. What I will do at the other side is start a new terminal because the SSH connection is broken. So at the right, we're starting to get these results of the calculation. I mean, it's gibberish, it's just data that we're sending through, right? But it's a good, you see essentially the timings of how fast we can do this. On this quite good machine is also the machine that we use to do heavy calculations upon. So with the FPGA, we can do the same thing. So at the moment, it's programming these FPGAs. This is a one-time thing. So this is this programmable hardware at the moment that is being programmed. It will take some time to be programmed, but it's a one-time thing that you have to do. And we will try to catch up with the other calculations. Let's see if it works. It's a live demo, as I said. It's always exciting. In the meantime, if there's any questions, but it's going to go quite fast, but if there's any questions already, yes? What is the for and the Sorry? What is the for and the this is, so, yeah, so the results are in. So I'll answer the question directly. So you can see with our hardware acceleration, we can really speed this up. And this is only our first prototype, right? We know how to speed this up. In a year, we will have a factor 10. I mean, and in the meantime, we will have continuous improvements on this. Yeah. So, and so the 4 and the 32 is the fact that we use 32 cores on the one machine, which we use 4 FPGAs. So it's a server with 4 FPGAs in there. We can use the setup. So, and this, I think, is really what's going to change FHE, right? We can already have this huge speed-ups. In the future, we will be able to do 10 times more in a year and 100 times more in 2 or 3 years. And this is going to really make FHE cost efficient. Any other questions? Okay. Yeah, we can wait and yeah.
What's sort of the cost of FPGAs nowadays, like the range or the ballpark?
Furkan can give the exact cost of FPGA.
So one of these FPGAs are around like 4,000 euros, and if you rent them, I mean, you don't have to buy them, you can just rent them on AWS. That's also one option that you can go for, and of course the server price a bit higher, but in the end you get this acceleration. So when you do the AWS comparison, we always compare not the CPU with or without FPGA, but compare it with one of the 192 core CPUs versus FPGA instances. There, FPGA instances are much cheaper than those IM CPUs or those with the GPUs.
So just to give a comparison, the CPU that is used to do this benchmarking for the multiplication, for example, for Zama, is a 30,000 euro machine or $30,000 machine. While our FPGAs is 4,000, but we use 4 of them, so 16,000 setup. So the setup cost of this is like half. We can also do 8 FPGAs or more, but at the moment we just have 4 FPGAs in this one server, so that's why we do 4. Yeah, Nigel?
Probably the best metric is to actually have AWS costs.
Yeah, so we have comparisons.
For every operation, this is the cost with AWS CPUs. This is the cost of the same operation with AWS. Because then you're kind of factoring out, AWS have already factored out the management costs, the install costs, the electricity costs, the cooling costs, everything, all in one price.
And that number is 3.4. So at the moment we're 3.4 times cheaper. And of course, if we have this 10x speed up in the next year, it will be 34 times cheaper. Because I think in software, we're hitting the limits. GPU, we will improve a bit more. I think maybe Nigel knows more, but we will improve a bit more with GPU, but also there we're hitting the end. I mean, people have been working on CPU for longer time, right? So we're hitting the capacity of CPU improvements. And FPGA, we really think another factor 10 is possible, and then you go to a chip and then you gain another factor 10, but that's more in the future because essentially the parameters have to settle. Like everything is changing. There's a new version of, for example, the Zama library. The parameters have changed, and if you want to have an efficient chip, you don't want to have like a new chip every month, because anyhow it takes 6 months for the chips to arrive, so yeah. But yeah, it's 3.4 times cheaper at the moment, and in a year it will be 34 times cheaper. That's essentially the numbers we have right now. Yeah.
And so for any changes on the library side, do you have to just upgrade the software, or do you have to upgrade the hardware as well?
Yeah, so we have to update the hardware. I mean, the hardware is really optimized for that, but it's all automized. So if you have a new, we have a script that computes all of this, and this is the cool thing about FPGA. So you have a new parameter set. Then it takes about like a week, I would say, to push out a new version. Yeah, and that just replaces. Also, if we have a new version that is fast, so we can also just push the new version. That's the cool thing. Yeah.
I have a question regarding the security, because I don't know about like FPGA that much, but is there like any security concerns where when you try to implement the algorithm in the FPGA, because for example like side channel attacks where you get analyzed explicit or something like that?
Well, maybe repeat the question, or did everybody hear the question?
I can repeat my question. So yeah, thank you. I have a question regarding the security concerns because is there like any security concerns regarding implementing the FHE in the FPGA? Because, for example, in CPU and GPU, maybe you can also do some side channel attacks. Is there like any security concerns that arise when you try to implement it in this new kind of processor? Yeah.
Yeah, typically for crypto, for everybody, like there's this attacks that you can do if somebody implements things in the wrong way. There is attacks where you can break the scheme. Now this is really cool, right? Because you encrypt your data, you send it to me, and I do computations. Now remember, this is FHE, right? Your data is encrypted, so I cannot get to the data, which means that even if you do a side channel attack, I mean, if I cannot get to the data and have all the information, you can do any attack that you want. You should also not get access to the data, right? So the really cool thing is that, I mean, if you do your encryption right, which is not that hard to do, but still, let experts do this for you. Don't do your own encryption. But we do not do your encryption, right? You do it on your computer. You send the data to us, and by the time the data is sent to us, it's encrypted. We cannot get access to this, which means that any other party that does any cool attack that exists will not be able to get to the data. So security is not a concern. We just need to be correct. The correct result needs to come out of there. But security is not a concern.
Thanks for the presentation. Any reason that you chose the FHE to start with, the acceleration over other libraries?
Yeah. So we have worked on the others. Like there's two main branches. I don't know how much you know about FHE, but there's two main branches. There's the FHE and the BGV CKKS, like bigger schemes. So we believe in the FHE because it's kind of the size is perfect for hardware. There is hardware being developed for these bigger things, but these are huge projects. And by the time we get these huge projects like correct, I mean, this will take a lot of time. And I think to bootstrap this process, TFHE is like the perfect size where it's, I mean, it's still difficult to do, don't get me wrong, but it's kind of manageable in another way. Like we can put it on one FPGA. With the bigger schemes, forget it. You need to build your own chip, which means it's half a year. These chips are gigantic, which means a lot of time. There will be problems with these chips. So yeah, in the future, I see like hardware on this for these other things, but it's not there yet. And if we want hardware for any FHE scheme, the FHE is really the one that we should go with first because it's the more graspable one, I would say, at the moment.
Makes sense. And the follow-up maybe. You are expecting like in a year to see this 10x speed up.
Yeah.
Is it like due to parallelization or like due to other breakthroughs?
There's a few things. So there's, for example, clock speed increase. So what we aimed for in this first version is really have like a working version that we can start to work with, that we can feedback from people what is important, integrated. But we can, for example, increase the clock speed by improving like the layout. There's some places where we can reduce the area a bit more because we've not done it like in the optimal way. So all of this, if you add them up, it's like a factor 2 because of the clock speed, which is quite low at the moment. There's a factor 2 because if we decrease the area a bit, we can double the parallelism on chip. And there's a few of these really easy gains that we can still do on FPGA. And then another cool thing that's not in the 10x, I would say, is that there's this new architectures coming out for AI, which focus heavily on like multiplications. We have, they will arrive in a few weeks, and so we will play with them, and maybe there will even be more speed up because of these really cool new architectures. But this is not in the 10x. The 10x is something that we're quite sure of. The new architectures we have to play with before we can say how much we can gain there.
Actually, I think you're being rather conservative with the 10x because with Xamarin, if you look at our run times, we get a factor 10 improvement over every year for the last 2 years.
Yeah.
So if you just factor in the algorithmic improvements, you get a factor 10, then you factor in your better hardware. I would say you're probably talking in 2 years' time well over a factor 100 improvement. So, you know, this is when you just add every improvement, 'cause it's not just, you know, Peter's talking about improvements in the hardware, but you also got improvements in the algorithms, improvements in the way the compilers work, improvements in just, you know, what we know how to do, improvements in the crypto, like, yeah, easily a factor 100 within 18 months.
Yeah, I think that's true, right? We're talking about hardware, but maybe I should split this off. Like, there's the hardware thing where we improve versus CPU, but of course, yeah, if you, one of the things, if you translate programs to FHE, you can really gain something there. That's also something that Zama is working at, we're looking at a bit. There's more things where you can gain. That's indeed an interesting thing.
All right, that's awesome. Bullish, 100x, we're all expecting that. So thank you so much, Pieter. Next we have Michael from Fabric.